Hey everyone, welcome back to Mind Maths with Amina. Today I'm going to continue solving the practice questions given in the Mathematics 1 study guide. This study guide is provided by University of London for the EMFSS courses, and the chapter is called Functions of Several Variables. Okay, the question goes as follows. A student has a part-time job in a restaurant. For this, she is paid $8 per hour. Her utility function for earning I dollars and spending S hours studying is this much. Okay. The utility function is a measure of the usefulness or worth to the student of a certain combination of money and study time. The total amount of time she spends each week working in the restaurant and studying is, 100 hours. Okay, first of all, let's set up a ratio, R's to her income. In 1 hour, she earns $8, which means in 1/8 of an hour, she'll earn $1. Therefore, she'll earn I amount of dollars in I by 8 hours. Okay, so I by 8 amount of hours she's put into earning money and S into studying, and she has a total of 100 hours. Okay, so we want to maximize utility, which depends on earning and time studying, and it's subject to this constraint. It's a time constraint. Okay, so let's formulate the Lagrange. It will depend on earning and time studying and one multiplier because we have one constraint. So we want to maximize this function subject to the constraint 100 minus I over 8 minus S. Okay, we want to take the derivative with respect to I and put it equals to a 0. And we want to take the derivative with S and put it equals to a 0, and derivative with lambda and put it equals to a 0. The derivative with respect to I and putting into it is equals to 0 will give us a 1 by 4 I power minus 3 by 4 S 3 by 4 minus lambda over 8 is equals to a 0, or we could just write it like this. Okay, so which becomes a 2 into a I 3 by 4 is equals to, let's call this equation 1. Okay, moving on, the derivative with respect to S, putting it equals to a 0, is a 3 by 4 I power, actually it's 1 by 4, and S minus 1 by 4, and then we'll get a minus lambda is equals to a 0, or just is equals to. Okay, this is equation 2. And equation 3 is simply our constraint, because when we take the derivative with respect to the multiplier, we just get the constraint back. Okay, so the first step will be to equate equation 1 and 2. And when we do that, we'll have this. We'll have this expression is equals to this expression. They're both equals to the multiplier. Okay, we have actually I can't do that, how dumb. Okay, 4 2s are 8, and S power 3 over 4 plus 1 over 4, and we'll get a 3I 1 over 4 plus a 3 by 4. So we have a 8S is equals to 3I. So basically you could write I is equals to 8S over 3. Call this equation 4. And now we need to basically solve these together. Okay, now let's do that. We have an investment over, okay, so 1 over 8 multiplied by I is a 8S over 3 plus S is equals to 100 8 gets cancelled. That's a 1 by 3 plus a 1. So a 1 by 3 plus a 1 will be a 4 by 3. S is equals to 100. So S star is going to be, actually let's just divide by 2. 2 2s are 4, 2 5s are 10, 0 0. So we'll have a 50 into 3 over a 2. So that's a 25 multiplied by 3, which is a 75. Okay. Then income would be 8 into 75 divided by a 3, which gives us, let me see, actually, let me take my calculator out. 8 multiplied by 75 is a 600, by 3, a 200. Okay. So basically, this person should spend 75 hours studying, and they'll earn $200. Okay, so that means how much will they be? 200 by 8. Okay, so therefore they'll be spending 200 over an 8 in working, which is a 25. So basically hours. So he's studying for how many hours? 75 hours. And working for 25 hours. And thus earning $200. So, and the maximum value function given our constraint, which was 100. So given the constraint, let's just call it the amount of the time that we had, let's call it t, is that we put the values of the optimal values of I and S into the utility function, and the utility function was I power 1 by 4, S power 3 by 4. So that basically becomes a 200 power 1 by 4, and what was that, a 75 power 3 by 4. And that's the maximum value, that's the maximum utility, and which is known as the maximum value function. Maximum value function, which is basically the maximum utility that can be obtained given the constraint. Okay, next question. Okay, sample examination question 5.1. Let's try to do this. It says a function of two variables is defined for x and y are actually, you're not allowed to use 0. So anything outside the origin by this. Okay, so we have a f x y is equals to xy ln x square plus y square. They want us to find the partial derivatives. Okay, first we want to find the derivative of f with respect to x, which means you treat y as a constant. We have a product of two functions. Okay, so first I take the derivative of this function and keep the other one as it is. So I'm going to get, let me just highlight this. This is two functions u and v being multiplied. So just think of this as u and think of this as v. I want the derivative of u and v as it is, and then the derivative of v and u as it is. Okay, so that's kind of like, just don't write it like that, it's just rough work. Okay, any examiner will not appreciate that. Okay, so the derivative of u is a y, and I'm going to keep the other function as it is. And then we have an addition sign, the first function as it is, and the derivative of the second one, which is going to be an x square, y square. And the derivative of this with respect to x is just a 2x, okay? So I'm going to place that in the numerator. And there on, we should just simplify it. I'll write ln y x square plus y square is equal, 2x square y over an x square plus y square. Okay, now next let's just calculate the derivative of this with respect to an x again. So we want the partial derivative of f with respect to x, but we want the double derivative, okay? So that's fx with respect to x. Over here, we just have one function of x, okay? So y stays as it is, x square plus y comes in the denominator, and the derivative of this with respect to x is a 2x, so that comes in the numerator. Okay, plus, now unfortunately, we'll have to apply the quotient rule here. Let's do it. Okay, the denominator as it is into the derivative of the numerator, which is going to be a 4xy minus, I think I should just decrease the size of this. Where's it? Yeah, so that it fits. Minus the numerator as it is into the derivative of the denominator with respect to x, which is just a 2x over denominator square. So you can either leave the answer over here, or you could simplify it by writing this as 2xy, and let's just take a common denominator. Let's just have an x square plus y square whole square, the denominator. Okay, then we'll have a plus 4xy into x square plus y square minus 2x cube. Oh, actually it becomes a 4 then. To the 4x cube and y. Okay, so this becomes a 6xy. I'm saying 6, but I'm writing an 8. X square plus y square minus 4x cube y over this. Okay, I think we can just keep it over here then. It seems okay to leave it over here. Or you could simplify it further by opening it up, but will that do any good? Yeah, maybe it will actually. Because this becomes a 6x cube y, and then we'll have a plus 6xy cube minus 4x cube y, and therefore that kind of becomes further simplified into a 2x cube y plus 6xy cube over an x square plus y square. I wonder if we can simplify it further. We can, because we can take an x and a y common. So I will be left with an x square plus 2 3 the 6 and y square. Yeah, I think this is as far as we can take it. Okay, let's move on. Let's move on. Okay, this is the function. Let's take it down. Okay, we want now f with respect to a y okay, f with respect to y, u as it is into the derivative of v plus v as it is into the derivative of u with respect to y will be an x. So we have a 2xy squared over x squared plus y squared plus x ln x squared plus y squared. Okay, so the second derivative again, if we take with respect to fy again, so fy with respect to y, we'll have to do the quotient rule here. So we'll have the denominator as it is into the derivative of numerator with respect to y, which is the 4xy, minus the numerator as it is into the derivative of the denominator with respect to y, which is a 2y, over x squared plus y squared whole square. Okay. And over here we have only one function of y, so x squared remains there. We get an x squared plus y squared in the denominator, and then in the numerator you'll get a 2y. Again, you can simplify this like we did for fx with respect to x, but we can just leave it here for now. You get the gist. Like, the important thing is being able to calculate the derivative. So I guess this is enough for this class, and we'll solve more questions in the next one. Take care.